Okay, so let's get started with transient stability. In previous lecture, we have already seen the intro of it, that whenever a disturbance in delta t is very large, at that point in time we talk about transient stability, the first thing. And we have also seen that in transient stability we talk about equal area criteria. Okay, so this we have already seen. Today we will talk about equal area criteria in detail. So whenever there is fault, there will be three cases, right? Pre-fault, during fault, and post-fault. And roughly the graph for pre, post, and during fault would be in this manner. That pre-fault Pmax will be maximum, during fault it will be minimum, and when fault is cleared, it will be somewhere between. One more thing, that Pmax is inversely proportional to x. So from this particular graph, what we can say? That x1 is less than x3 is less than x2. Okay, so this can also be the kind of question coming in exam. Basically what I am trying to say is, post fault clearance, that is P max 3, will lie between PM1 and PM2. Fair? Fine, so let's get started. In pre-fault, basically what I'm trying to tell is, in pre-fault, you will see a point which get equated to your shaft power. Okay, that is, let's say this is your shaft power. So this angle will be del naught. P is equals to EV upon x1 side del naught. Okay, from that you will be able to get del naught. During fault, similarly there will be there will be fault. The same formula of P max 2 sine delta some x would be coming. For post fault also, P is equals to P max sine del something would come. So let's remember that the formulas which we write are for PA and not for PM. PM is constant. Shaft power is constant. What will be changing is, depending upon the state of fault, whether it's pre, during or post, our PE would change. Some important things to take care is, initially before fault, for steady state stability, P will be equals to PM. Okay. Also after fault, after clearing the fault, we will be swinging. There will be swing in P3 curve till the point you reach to PM again. Okay. That meaning it will accelerate and then deaccelerate. It would reach to PM again, and that would be called as point of at that particular state, basically your fault will be cleared, and that will be called as P max. Okay, so at at del max, PM3 will be equal to again PM. Okay, and at del naught, your PM1 will be equals to PM. Let's be very clear on this too. Okay, but del max you won't be able to calculate directly. So del max, depending upon case, del max will be either pi minus del 1 or del max would be pi minus del 0. Let's see, that will be case dependent. We will get to know that soon. But what I am trying to tell is this particular point, that P is equals to P max, P is equals to PM in two cases. After clearing the fault, before it settles down, that is PM3 at some PM3 sine delta at some point or other should becomes to equal to PM, and PM1 sine delta should also becomes to PM initially before fault. So these are two things to be taken care. Now let's get started with the analysis. So as I have already told, initially pre-fault condition में PM will be equals to P max 1 sine delta naught. From here you will get delta naught. After fault, basically after fault settled down, again your at some point or another, your P max 3 should be equals to PM. That should be P max 3 should be equal to P max 3 sine delta should be equals to PM, and that is nothing but will be equal to some angle. So let's say delta 1. Let's say it get equals to at delta max, but then there will be two deltas which it will be passing. Since it is a bell type of thing, there will be 2 points. So what we will be doing is, we'll be calculating initial point, and then maximum will be doing as pi minus delta initial. Okay. So what we'll be doing here, it won't be delta max, rather it will be delta 1. We'll be getting delta 1 here after fault, Pm upon sine inverse Pmax, and then we'll be doing pi minus delta 1 or pi minus delta 0 depending upon the case we are working upon. We will see the cases very shortly. Okay, now let's move to equal area criteria. So in equal area criteria, there are two formats of it. In transient, basically d del upon dt will be equals to nothing but 2 upon m pa d del. Okay, that will be some value when there is transient during fault condition. When it is steady state, that is pre and post fault, this area under curve PA d del, there will be no acceleration. That's why integration of PA d del will be equals to 0. Fine. Now let's see one of the important formulas. One is critical clearing angle and one is critical clearing time. These are very important formulas, and depending upon the cases, again we will be substituting the values of del max, we'll be substituting the values of P2, PM and so on in this particular del CR formula. So what is del CR? Del CR is nothing but cos inverse P shaft into del max minus del naught plus PM3 cos del max minus PM2 cos del 0 upon PM3 minus PM2. Fair? This is nothing but formula for del CR. Okay, and TCR is what? TCR is nothing but 2m upon PA del CR minus del naught. Okay, if m and p are in units per unit, then what you will be doing? You will be doing nothing but h upon pi f PA per unit. Okay, same del CR minus del naught. So you need to check very properly always whether m is given, whether p powers are given in per unit, whether their actual values are given and so on. So let's quickly revise these formulas. Equal area criteria, D, there are two formulas of it: during fault and steady state, that is pre and post fault. During the fault, d del upon del t is nothing but root of 2 upon m integration PA d del equals to 0. In steady state, integration of PA d del equals to technically 0. Okay, and for del CR value, it is nothing but cos inverse P shaft del max minus del 0 plus PM3 cos of del max minus PM2 cos of del 0 upon PM3 minus PM1, and TCR is nothing but root of 2m upon PA into del CR minus del naught, and depending upon per unit or actual value, we would change the value of m accordingly. Fine. Now let's move ahead and see quickly frequent types of questions. So there are three types of questions. Let me quickly give an overview. So there can be questions where it is single line and fault occurs at bus. There is another kind of question when there are parallel lines and fault occur near bus. And third type of question is parallel lines and fault occurs in middle of bus. Okay. So we'll look at the first case. We'll look this in little detail, wherein fault occurs at bus for single line. Okay, so basically pre-fault, what this is a very constant, this is very constant graph. This you should always make P max 1. Okay, and there will be some P shaft power also. Let us make with some different color. So there will be some P shaft also. Now I have already told that this angle, this the first time where they both intersect, we call it as del naught. Now let's say fault has occurred. Now fault has occurred and that is only single transmission line. Since fault has occurred, PE will drop down to 0. So you see del naught you calculated here. Now P is dropped to 0. We know that PM minus P is nothing but P acceleration. P is 0, matlab PA is positive. It is in acceleration state, meaning del will keep on increasing. At some point or another, fault will be cleared. Once fault is cleared, it will move back to the graph. Since there is one line only, x will not change, x effective will not change. Again, once same x will be activated, once same x is activated, Pmax will be same, so it will jump up. It will jump up. It will further accelerate. At a point, it will decelerate, and then certainly at a point it will stop. It will stop. We have already seen, right, when this point comes, where both the Pmax 3, now what happens is, now Pmax 1 is nothing but equals to Pmax 3. since effective x is equal. The reason is, since x effective pre and post is same, pre and post is same, okay, pre and post is same. P max 3 is same to P max 1. Now this point where again P shaft is nothing but equals to P max 3 is nothing but equals to del max. Now we can clearly see that this value is equal to this value. So we can call del max as pi minus del naught. Okay, so now you know del naught, you know del max, you know both the things. Since you both know both the things, you can find out del CR. Once you know del CR, you can find out TCR. Okay, that's all. That's all. Now coming to case 2, wherein where there are two parallel lines and fault occurs at the bus. So let's first discuss that pre-fault x will be, let's say, some x will be nothing but 1. Okay, during fault what happens, we technically don't care, p becomes 0. This is pre-fault. Okay, pre-fault nothing but ev upon 1. Post fault what happens, you will clean this line up, so your x would increase from 1 to 2, x becomes 2. So post fault what happens is ev becomes nothing but 2. That is, so basically what happens is you will first of all, so as we have said already, that your P max 1 would be always there, P max 1, and your shaft power also will be there, that is Pm. Fine, that is nothing but the intersection point is nothing but del naught. Now what happens is fault is occurred. Whenever fault is occurred, you will start moving downwards, but still acceleration is there, since Pm minus P is positive. Your del will keep increasing. Since P is 0, it will be on 0 x axis only. At some point or time, fault is cleared, but now what happens is, post fault P max 2 is less than P max 1, you can see here clearly. This is pre-fault, post fault. So P max 3 is less than P max 2. So now we will be having one more graph. P max 3 is less than, let's say, P max 2. Then what will happen? Your delta would increase. It would again settle. So there are 2 points again where you have intersected. So you have got del 1, you have got del 2 or del max, and the place where you cleared the fault is called as del CR. Now clearly del max is nothing but equals to pi minus del 1. In this particular case, it is nothing but equals to pi minus del 1. You know del naught, you know del max. If you know this too, you can clearly find out del CR using the formula. If you know del CR, again del TR can be found out. So that's what is written here. Okay, you will equate P max to Pm at some point. That will give you the value of del 1. Once you get del 1, you can get pi minus del 1 is nothing but del max. Del 0 is already known. The point to take care is here Pm2 is equals to 0. Fine. So while using del CR formula, you will be making Pm2 to be 0. Now let's say when the fault is in the middle of transmission, in that case Pm2 is not equal to 0. It will be minimum but not equals to 0. So same you can see in the graph also. So let's say this is Pm1. Okay, this is Pm1. This is P shaft. So this is nothing but delta naught. Okay, now let's say fault is occurred. So this is nothing but during fault. Now what happens is, since there is a fault, you will start traversing. Now fault is cleared. There is the effective resistance would go down. So now your graph during would be this, post would be this. Now this is P max 2. Okay, P max 3 actually. Now what? P max 3, it has intersected at 2 points. So this is nothing but del 1. This is nothing but del max. Del max is nothing but pi minus del 1. And the place where you are clearing is nothing but del CR. So again, del naught and del max you have. Del CR can be found out. TCR can be found out. And in this way, with this 3 cases, you can go through them. I'll clear them. You can go through them thoroughly, and you can try solving these 3 cases one more time in your rough book, or try recalling them. That will help us. Okay, we should only be taking care about del naught. We should be looking at what happens during the fault, and we should look into the del max condition. So del naught, del max, and what happens during fault, whether Pm2 becomes 0 or not. okay, or what exactly happens is to be taken care. I'm just waiting here so that you can take snap of this particular case when it is near the bus and single line. We can look at the second case properly when it is near bus but there are two lines. And then the final case is when it is in the middle of transmission line of parallel lines. Okay, so you can take a look at that, and here we can wrap. So this lesson was very simple. It had nothing much. It had nothing much. It was simply pre-fault, during fault, post-fault analysis, and we saw equal area criteria that d del upon dt is equals to root 2m upon pa into integration of pa d del. That is during fault. At steady state that will be 0. In turn, integration of pa d del d del becomes 0. And we saw formula of delta cr and tcr. So delta cr is nothing but cos inverse ps into del max minus del 0 plus pm3 cos del max minus pm2 cos del 0 upon pm3 minus pm2, and tcr is nothing but root of tm upon pa into del cr minus del naught. When actual values are given in per unit, that becomes m becomes h upon pi f. Fine, that's all about this lesson. Thank you.